Mindsetters, welcome to Learn Extra Live. I'm Katleho and this is Tracy.
Hello, Katleho. How are you?
I'm great, thanks. How are you, Tracy?
Good, thank you.
What a stunning day it is.
It is. Unfortunately, though, some matrics are at home studying.
I know, which is even better. That's why we have exam school. And today we are doing physical science revision, guys, just for you. How do you feel about that? It's absolutely amazing.
It's brilliant because I know they need it.
Yes.
Physics was yesterday and it's come and gone. So, guys, no matter whether it was good, bad, or ugly, or anywhere in between, it's done. It's over.
Done.
Nothing much you can do about it now. In fact,
Except study for the next one.
Absolutely.
Tell us what we'll be doing today.
Well, just like with the last program, it's live, so we'll take your questions. We've got a couple lined up already, looking at past papers, because we really need you to tell us what you need us to do. So,
of course.
Anything to do with chemistry, okay? No physics.
No,
we will
yeah,
not
'cause
answer
in the
physics.
past, of
Physics
course.
is gone.
Yes.
So I'm afraid if you aren't at a government school or you're not doing the government curriculum, I'm afraid you're going to have to deal with us because we're doing chemistry. So we're focusing on chemistry for today, and we'll see how it goes.
Thank you, Tracy.
Yeah.
Thank you. You can go over to your
Thank
board.
you.
So, guys, of course, you heard exactly what Tracy said. She needs to hear from you guys. She needs you guys to guide her into what she'll be doing today. So please make sure that you send in your questions or answers on what Tracy will be doing, or any queries that you may have on our Facebook page, facebook.com/learnextra, and our Twitter handle is @learnextra. Guys, today is really, really awesome because it is the day after your physics paper. Please tell me how it went. Actually, I would really love to hear how that paper went. And it's a few days away from your chemistry paper. So make sure that you are absolutely on the ball today. And I also want to remind you that our exam school booklets are on the website for you guys to purchase and to download. So make sure that you are doing that right now. Send through anything that you need to send through, guys. Make sure that you're with us today, 100%. And of course, Tracy's going to let you know about our Mixed Curio. Some of you have been a bit confused, but don't worry. We'll be here for you the entire show to guide you through it, as well as to guide you through anything else that you may need in the world, guys. Make sure that you post it right on the page. Over to you, Tracy.
Thank you. All right, so guys, Katleho mentioned, one day I'll actually say your name right.
Maybe.
Mentioned that we got some stuff on Mix It in the Curio portion of it. Okay, this is great. I love this platform, and it's so good. It's a nice way for you to do quick revision on a whole bunch of stuff. So first of all, we need to go through, particularly if you are a first-time user, okay? So you go to your phone, you open up Mix It like you would normally, and then you need to go to Add Contacts, because this has to go into there. You need to select Add Contact manually within Mix It. So it's not going to find it for you. You've got to add it in manually. All right. Then you, in the ID text box, you need to enter in qa.ed.ge. Okay? qa.ed.ge. Okay? You got that into the text box. Then you need to send the invitation and finish. So you go scroll down to where you get the little blue button. Finish. Okay. Then you're not done. That's only step 1. Step 2, you now need to register on the Curio page. So within Mix It, so you go to your apps menu, in Mix It, okay, not your general phone apps menu, the Mix It apps menu, and under general apps in the Mix It menu, you find your new app, which is qa.ed.ge, okay, and it will be there, but now you need to register. So before you can start using the platform, you need to register. So now you click on it, okay, make sure you open it, then you're going to enter your name and enter your mobile number and send it. Follow the instructions. So you enter your name, your mobile number, and then an SMS is going to be sent to your phone. You need to open that SMS and get your login code. Okay, that's like a password. So there's a confirmation SMS that will be sent to you at no cost to you. That's all been sponsored, okay, so you don't need to worry about that. Get your login code. You then go back into Mix It, open Curios again, get to qa.ed.ge, and put in your login code where it asks you for it. Okay. Then once you've logged in, you'll go to the home page. Okay, so for those of you who have already got Curio, those of you who have now signed up, registered, all the rest of it, you now open the Curio page, and now you need to enter in the code. Today's code, okay, for example, is PSI 25. There's actually 4 assignments on the homepage at the moment. You've got to do the whole assignment and then send it, okay? When you answered all of them, click submit. It'll come through to us. Now, why is this important? Because I heard some very important news today that you didn't know. Very exciting for the maths.
Tell me.
There are competitions about the career page next week.
Awesome.
With very, very, very cool prizes.
So make sure that you are
So
on
get
top
using
of
it,
that.
okay? Very, very cool prizes. So we're just making sure you know how to use it so you guys have got a head start. Okay. Now, today's codes have disappeared. Okay, they're not on here, but there's, if you look, I will get them for you, but there's PSCI 25, 26, 27, and 28, okay? Today's assignments look at redox, they look at grade 11 chemistry that is needed for grade 12, it looks at some organic stuff, and it looks at equilibrium. There's only 5 or so questions now, not 10, so it's quite easy for you to get through. Spend your time. This is such a nice way to do revision. Multiple choice, as much as a lot of you think, oh, it's a little bit of a monkey puzzle and multiple guess and just great way to revise, great way to really see if you understand your work. So get onto the page, make a plan to do it, on Mixit. You guys all know how to use Mixit, okay? It's old toppies like me who go, what? I'm barely learning how to use BBM right now.
On.
I have my moments. I never got into Mixit. I WhatsApp and with Mixit not so much, but you guys, brilliant. Nice platform, nice, easy platform to use, okay? So get going with Curio. Okay, I'm hoping that's cleared up some of the confusion, okay? So get going. We will make sure we get what the codes all mean. I think we'll have to put it up on the Facebook page.
Yes.
For some reason it didn't come up here, but that's fine. Let's jump straight into what we want to look at today, okay? So what we're going to look at is we're going to look at equilibrium, and I can hear the groans because you're all going, no. Guys, equilibrium is a guaranteed section, okay? I promise you, you are going to get equilibrium. Equilibrium is going to end up being description questions based on the chateliers, okay? Whether you can tell which way the equilibrium gets shift, whether you can tell why it shifts, all of that sort of thing. And then it's going to be a KC calculation, your equilibrium constant. Equilibrium constants generally all the same, though this question, which was taken from the Eastern Cape prelim paper, is a really nice one. I gave it to my learners at school, and the first thing they wanted to do was draw a table, because that's what you all get taught, and that's great. You see, oh, I see equilibrium has to be the table. We're going to look at one of those in a second, but you must read all the information given to you before you just jump in and go, oh, it's got to be a table. Though, if you do start drawing a table, start filling it in, and you realize, wow, there's something wrong with the information I've been given, then look at another method. You don't always have to use the table. So it says to you, the following reaction reaches equilibrium in a closed container. So that's an important word here because it's a closed container. Remember, it has to be at a closed container at a fixed temperature. And remember, it has to be at a fixed temperature because temperature affects equilibrium. If I change the temperature, I change the equilibrium constant. Oh, look, it's SO3. It's the reverse of how we normally see this. Because normally we see this as SO2 plus O2 goes to SO3, which is the catalytic oxidation of SO2, sulfur dioxide, which we need in the contact process. Okay, but now it's the reverse. Doesn't matter. At equilibrium, I want you to see a very important thing here. Normally, in these questions, if you're going to need to use the table, they will say to you, initially, we have this and that and that. Then, the system's allowed to reach equilibrium, and now we have this. We have so many moles, volume, whatever the case may be. They didn't say that to you. They said at equilibrium. It's already got this, like finding the last line of that table. They say to us that the concentration, remember square brackets being concentration, the concentration of the SO3 is 0.04, the concentration of the SO2 is 0.5, the mass, okay, that's a bit interesting, of the O2 is 19.2 grams, and the Kc value is 31.25. Calculate the volume of the container. Okay. Let's think about this. They've given you a Kc value. They gave us 2 concentrations. That's nice, that's easy, because Kc value works on concentration. And they gave us the mass of the O2. So now we can say to ourselves, okay, volume, O2 needs to be converted to concentration to be able to use it in my Kc value. So if I go down a little bit, we remember and we say, well, concentration is number of moles over volume. So think about what we need for the oxygen. We need to know its concentration in order to get its volume. I can work out number of moles, of course I can, because I know the mass given, but we also have this equation that says that we can use little m over m times v, okay? So, let's do this in 2 parts. First step is we're going to find the concentration of the O2 by using the Kc value. Step 1, we need to write an expression. So, my Kc value is equal to, now remember, it's the concentration of the products divided by the concentration of the reactants, okay? Guys, please be careful, do not write concentration of products divided by concentration of reactants. That is not an equation, it's a memory guide, okay? Remember, the coefficients at the top, so we've got to make sure it's balanced, those become our exponents. So that means this Kc expression is going to be the concentration of sulfur dioxide, all squared, times by the concentration of oxygen, which we don't have to square, divided by the concentration of SO3, all squared. Okay, so we are doing quite well at the moment. Let's see what we can fill in. Well, the Kc value is 31.25. SO2 was 0.5. O2 is what I don't have. And SO3 was 0.04. Okay. Concentration of oxygen, we can find it by going, well, O2, and I take the 0.04 squared over to the top, we take the 0.5 over, and I've got random values running around on my board, because that never happens with me. Okay. All right. So now this is when you have to make sure that you've actually got things open that you were supposed to have open, because, and now you go looking for your calculator, because you should have opened it. And the only reason why I'm looking for my calculator, grade 12, is I'm actually doing this a different way to what I did it in my notes when I set it up for you guys. So we're just waiting for it to open up, okay? And the reason being is what I did, and the math becomes a little more difficult, is I actually put this concentration equals m over m into this equation straight away. Let's not get ourselves into it as over that. So there we go. Come on, there we go. So 31.25 d times 0.04 squared. Okay, gives us 1 over 20, don't worry about that, divided by 0.5. Oh, didn't like that. Gives us 0.1. Okay? So, this is equal to 0.1 moles per decimeter cubed, but that's not what they wanted. They wanted volume, so let's go back here. This is 0.1. The mass they told you was 19.2. What is the mass of oxygen? Okay, you need to know this. It's going to be 36. No, 32, because it's 16. Okay, so it's 32. And we want the volume. So volume, we're going to swap those around, becomes 19. Yes, you see. Okay. We need to go back because I have a very clever director who's reminded me of something. Because, you know, sometimes, guys, you get into such a hurry, and I forgot to square the SO2. Okay, that's huge, okay? So, just so you know, we all make mistakes. That's why you go back and check. So let's just change that. Let's do it here. Let's find the answer again. Okay, so let's start again. 31.25 times 0.04 squared equals, divided by 0.5 squared equals, much better, 0.2. Okay, that looks better as an answer anyway. Okay, moles per deth. Oh, that's just hideous writing, but that's okay. So that's 0.2. That's 32. We're going to times by 0.2. Okay. Let's go back here. All right, so 19.2 divided by 32 times 0.2. And we get 3 as our answer. Okay, so guys, the point is, you are welcome to do this in one step. So you're welcome to put the volume into here if you really, really want to. It's just that then you're dealing with a fraction. That fraction can get quite complicated. Okay, just be careful. Don't do what I just did, which is forget out the square along the way. Okay, work slowly. Very important. Nice thing about this is it's worth 8 marks, and a lot of the times you guys go, oh, it's 8 marks, it's got to be a table. Not necessarily. It's worth 8 marks because of the calculation from the volume. Okay, so grade 12s, I think it's time for you guys to have a break. We've got a lot of information. Make sure you get onto Curio. And then Phil will actually come in just now and do something else.
Yeah. So you're going to transform, basically?
I am.
Okay.
Yeah. You see, on Wednesday it was Tracy and Tracy. So I think we got a little confusing.
Okay, then, yeah. And
we were
now
both
it's
Tracy.
Actually, that's not confusing.
It is because we look different.
Yeah, no, that's why it's not confusing. Because it's
okay.
the same name, then we don't have to remember Phil and,
Yeah,
you know what I mean?
I understand.
Okay,
That's
so we're going to go for a break. You guys, during the break, obviously you can jump onto Curio. You can check out the page because I'm going to put up the question that Tracy has just done, just for your knowledge and just so you can repeat it also over the weekend. See you right after the break. Welcome back, Mindsetters. If you have just joined us, we are doing physical science today, and today we are focusing on chemistry. Your guys' physics paper was yesterday. I've heard a lot of remarks on it. I've heard that it was absolutely awesome, and that's fantastic, guys. That means that your focus this week was absolutely superb, and you guys studied to the T and you knew all your stuff. That's the only thing that makes an exam awesome. So make sure that you are here and you're focused today for chemistry, because that's also just a few days away. So make sure that you have joined us fully today, guys. Also, joining us means that your questions are up on the page right now. Send them through, guys. We are so keen to hear where you guys went wrong, or where do you think you're going to go wrong, just so that we can help you clear up those last things. Over to you, Phil.
Thanks so much, Kat. Okay, well, some of the questions that you guys have been sending in, we've been answering. There's a whole team of people busy answering the questions on the page. So I hope that's going well. And what I want to do is I'm actually going to run through some of the past paper questions that we've thought were particularly good. Now, rates of reactions. Now, remember, Tracy said that equations of, not equations of motion, you guys have done that. Okay, but equilibrium. Equilibrium is a guaranteed question. Now, this is another guaranteed question. The guaranteed question here is rate of reactions. Okay, so a very, very good way and a very, very common way of testing this type of question is in the form of an experiment. So we're going to read through an imaginary experiment, and here it goes. So it says a group of learners used the reaction between zinc and sulfuric acid to investigate one of the factors that affects the reaction rate. The equation below represents the reaction that takes place, and there it is. I've got my zinc. Just remember that zinc is a solid over there. I've got my H2SO4. The aqueous, that means that it's dilute, it's not concentrated. And then we've got our products on the other side. So I've got my zinc, which once again was a solid, and I've got my aqueous, or my dilute sulfuric acid. So very important to know which two things are mixing inside a chemical reaction, and then we can find out what's going on further. Okay, so let's get right into it. So it says that they add 6.5 grams of zinc granules to excess. Now, excess means that there's actually more than you need of dilute sulfuric acid. Then they measure the mass of zinc used per unit time. So I'm going to be following the mass of zinc as it changes over time. So it says the mass of zinc. There we go. That's what we're following, used per unit time. Okay. Now, all of a sudden, we start to see that there's various things that we can measure, various things which we can follow, and those become my variables. We might be asked those at a later stage. Now, it says, the learners then repeat the experiment using concentrated sulfuric acid. So that's something else which they changed. I've done 2 experiments. What did I change from one experiment to the next? Well, I kept the mass the same, but it seems like in the second experiment that I used concentrated sulfuric acid instead of dilute. So now we've got to define the term reaction rate. Now, I'm going to give you a little bit of a tip, and you might have actually picked this up while you were studying physics. A lot of your definitions which contain this word rate means that it's got something to do with time. And now, if I was to calculate rate, it's quite easy to remember that there's a formula that says that rate is equal to the change in mass over the change in time. Now, that mass can be reactants or it can be products, so let's actually write this out in a sentence. So the rate of a reaction is how much mass is gained or lost of a reactant per unit time. Now, that's a lot to think about. So let's write that out for you guys taking notes. So rate is, here we go. It's the mass of reactant used. Now, it can be product gained, but mass of reactant used, there we go, per unit time. Now, that means that we can have it per minute or per second, and we can go from there. It may actually tell me to calculate this later on. So it's the mass of reactants used per unit time. So I've got to have something which tells me the amount, and per unit time gives me the rate. Remember, when you divide by a change in time, that is the rate of something. Okay, so let's start to take a look at some of the questions involving the rate. So it says, give a reason why the acid must be in excess. Okay, now this is quite a weird word. It's not a word which I'd commonly use. Excess means that I have more than I need. So why must I have more acid than I actually need? Well, one of the things that we'd like to keep constant is we'd like the zinc to run out first. Why would we want that? Well, we want the acid's concentration to be the independent variable. So what I'm trying to say is that zinc must be the limiting reagent. So that must be a constant variable or a fixed variable. So zinc must be the limiting reagent. And that's quite important to know. And what else? We'd like to make sure that the acid doesn't run out before I've lost all the zinc. So this is why zinc must be the limiting reagent and not the acid. Because what's going to happen if the acid runs out first, it's not actually a fair test. That means that we haven't only changed one variable, but we've changed the total amount of reaction, and we've changed the rate, as well as the concentration, which we changed as our independent. Okay, so we've got to make sure that zinc must be the limiting reagent. HCl must last until the end of the reaction. So there we go. We must make sure that the HCl lasts. Okay, let's make sure that my English is correct there. There we go. So HCl must last because we want concentration to be the independent variable. So there we go. So concentration must be the independent variable. And if you're wondering how I decide which one is independent and which one is dependent, independent starts with the letter I. And I control the concentration. So concentration must be the independent. Now that means that I control that variable. So I control the concentration. That is the one that I take control of. I is the first letter of independent. Very nice, easy way to remember which one is independent and dependent. Let's see what else they ask in this question. Okay, there we go. All right, so now they're saying write down a hypothesis. Okay. This is also a very, very scientific word, a hypothesis for this investigation. Now, a hypothesis must have two things to be a good one. First of all, I must relate the two variables in my hypothesis. Then, the second part of a hypothesis is the way that I put it together. A hypothesis must be a testable prediction. So I must use the future tense when I start to speak about a hypothesis. Now, I know this sounds a little bit like an English lesson, but I'm going to show you the difference in what I'm saying. So remember that we are looking at concentration and we are looking at the reaction rate. Okay, so now we were told early on that my learners were trying to investigate something. So they were using the reaction between zinc and sulfuric acid to investigate the factors. So there's one of my variables, and that was concentration, that affects reaction rate. There's my two variables. The factor, which is concentration, and reaction rate. Now I must make a prediction about concentration and reaction rate. If you've been studying hard, this one shouldn't be too difficult. I know that an increased concentration will result in a higher reaction rate. So that's just a prediction. It doesn't actually matter if it's wrong. So increased concentration will. Now notice how I use the word will. I'm talking about the future tense. So the increased concentration will result, and we've got to mention the other variable to get my marks here, will result in a higher, there we go, a higher reaction rate. And that is a prediction, and it's got both variables. And that is what your examiner is looking for. Okay, moving along. We're doing pretty well here. So it tells me that I must give a reason why the learners must use the same amount of zinc granules in both experiments. Okay, now the reason that I must use the same amount of zinc granules is because zinc granules have a surface area. So if you change the number of zinc granules, what you can affect is the total mass of zinc. You can also affect the surface area of the zinc. And remember that surface area is one of the things which can affect reaction rate. So one of the reasons that we need to keep the number of zinc granules the same is to preserve or keep the surface area. So I need to keep the surface area the same. So I need to keep that surface area constant. That is a fixed or controlled variable. And remember, to have a fair test, to have an experiment which works, I must control all the variables except my independent and my dependent. So surface area is one of those things which can change the reaction rate. And we've got to control those types of variables. Otherwise, we're really going to run into a lot of trouble. Okay, now we're doing pretty well. We're moving along. There we go. So it says the results obtained for the reaction using dilute sulfuric acid are represented in the graph below. Okay, so let's navigate our way around these maps. Okay, now if you're thrown into an exam and you've never seen this graph before, where do you begin? And a lot of learners are saying, well, okay, how can I approach a graph that I've never seen? Here's the trick. I want you to concentrate on the y-axis first of all. What is it? And then we start to describe it in terms of the y. Let me show you what I mean. So if I've got the amount of zinc over here, that tells me how much of it I've got. These are my zinc granules. Now, let's just see what happens on the y-axis, and then we'll see how it happens. So I start out at a value of 0,1. If I want to know what I've got 0,1 moles. I'm told that because my y-axis has got a unit. So let's make sure that we understand what the y-axis is talking about before I actually move on. Now I'm going to describe the number of moles of zinc as time goes by. I notice that the value steadily drops as I move all the way through here. So it's going to be dropping all the way down there. So I know that that's something quite important. It's going to drop as time goes by. Now it's not always dropping at the same speed, but let's leave that for later on. Let's find out if we can figure out what it means for zinc to drop by a certain amount in a certain amount of time. So I've got my amount of zinc on my y-axis. I know how long it's taking, and I can actually start to navigate through my questions. So it says using the graph. I must use the graph. You cannot just thumbsuck values or just read them off. It says calculate the mass. Okay, so we're looking for M for mass, of zinc, which is used from t is equal to 0 seconds, so that means from the beginning, to t is equal to 60 seconds. Now I want you to take a look at the graph. Let's find those places and let's see how much zinc there is at 0 and at 60. So let's just switch colors and make sure that we know what we're doing there. So at 0 seconds, if I go and look at my y-axis, at 0 seconds, I find that there is 0.1 moles of zinc. Now, let's move across to 60 seconds. Let's see how much the mass is at 60 seconds, or at least the moles. And then we can find out the mass. If I know the moles, I can find the mass. So at 60 seconds, they've actually been very, very kind, and they've drawn in a dotted line. So what we're going to do is we're going to extend that up. So here we go. My dotted line starts to intercept there, and we can start to read off the y-axis. They've even told me what the value of the y-axis is at that point. That tells me that at 60 seconds, I've got 0.08 moles of zinc left. So I know how much I had in the beginning. I know how much I had in the end. So what I've got to do now is I've got to figure out how much mass that is. So let's take a look at what type of calculations we can perform. Okay, so running through our substitutions. Now, a lot of you were saying, okay, well, how do I figure out the mass of something using the number of moles? The manipulation that we can use, let's just make sure we make some space there. Okay, so the manipulation which we can use over there is that the mass is equal to the number of moles times by the molar mass, which I get off the table. The question is, where do we get the number of moles? Do I use 1 mole? Do I use 0.08? Neither. I'm going to use the difference between them, because they said how much is used, how much was the change in zinc moles. So what I'm going to do is I'm going to subtract those two values. So what I've got is the change in the number of moles of the zinc. So what's going to happen is I started out with 0.1, I subtracted from it what was left over, and that will tell me how much was used. So if you find the difference between them, that is how many moles we've got. The last thing to do is, where does a 65 come from? 65 is straight from my periodic table. So if I take my number of moles, I multiply it by my molar mass of zinc, and what I get is 1.3 grams. That is the difference in the mass of my zinc as the experiment goes. Let's just go through that calculation again. I find the change in the number of moles first, because I've got my initial amount and my final amount. This is how much is lost, because that is the difference between those values. So I can actually find out how much change in those moles we've got. That is the change between the initial and the final values of my moles. Once I know how many moles were used, I multiply by the molar mass, and I'll get 1.3 grams. Really, really challenging question. Very difficult, but not too bad. I'm pretty sure you guys can handle it. Okay, so just running through this question quickly. It's rates of reactions, definitely an experimental type of question. I'm not sure if we've got a little bit of time to answer one teeny tiny question. What do you think, Kat?
Maybe we do. Teeny tiny.
Okay, let's
one.
make sure that we make this a very, very quick one.
Okay.
Okay, this just follows on from the next one. Sorry, it follows on from those 2 points. It's just to make sure that we complete. Remember that this is a graph. And they've asked me to actually calculate over here the average rate of reaction in grams per second. I'm going to show you how to do that quickly. All that I need is the change in mass over the change in time. Now, funnily enough, that's actually changed my triangle. So let's make sure that that is a triangle. There we go. It's the change in mass over time. Well, since we calculated our change in mass is 1.3, and the time that it takes is 60 seconds, I can find that this is 0.02 grams per second. Not too tough if you practice through it and make sure that you read your graphs correctly. Over to you, Kat.
Thank you, Phil. Phil, someone just said that they love you and they wish you were their teacher.
Oh, well,
That's
thank you
awesome.
so much for that.
So, guys, we're going to take a really quick break. During this break, remember that there is some curio answers still to go through, and we need your questions, guys. Send us through anything that you need to know. Anything, guys. When I say anything, I mean anything on what Phil has done, though. See you right after the break. welcome back, Mindsetters. Physical science has really been amazing today. We are doing chemistry revision, and we are still waiting for some questions that you guys have on what Tracy and Phil have done. In case you're wondering, just in case you're wondering, all the questions are on the page. You're not seeing wrong. They are on the page, and you guys can save them onto your phones, onto your laptops, your computers, your parents' computers, print them out, post them on your walls, in the bathrooms, in your sisters' and brothers' rooms, in the kitchen, everywhere that you need to post them, just so that you guys can do extremely well for your chemistry exam, like you've done well for your physics one. I trust that it was an awesome exam, as you guys have mentioned. So good luck for the chemistry one. That's what we have for. Over to you.
Thank you, Katlego. I'm not sure about the brothers and sisters room.
Why not?
Well, I know if I'd done that to my brother, he would have actually just sat on me. But that's besides the point.
That's you.
But he was also older than me. I love him now, but back then we weren't good friends.
Okay,
Anyway,
your
moving
younger
on.
brothers. It should be younger brothers then.
Yeah.
Maybe.
Anyway, moving on. Okay. Guys, it really seems like we know that equilibrium is an issue for you guys. So we can going to another equilibrium question. This was a bit of a doozy. It's quite a hard one. And it's from the November 2010, question 7. Okay. I'm sure you saw we were looking at rates a little stoichiometry before with Phil. So now we're looking at another equilibrium question. And this one is a table format question. Once again, it's one of those where it's not difficult from the equilibrium point of view. It's horrible from a maths point of view, okay? So stick with me, all right? Don't get lost. Let's do it step by step, and you'll see it's like all the others you've did. It's just the last section with the maths that it's not so nice. Okay, so they tell you the reaction is investigated on a small scale in a laboratory. It's 7.5. It's part of another question, okay? Initially, remember I said to you keyword initially. So initially, 4 moles of SO2 and an unknown mass, okay, unknown mass of O2 are sealed in a 2 decimeter cubed flask. Great, we know we're not going to have to work out volume. They're allowed to reach equilibrium at a certain temperature. At equilibrium, it is then found that let me get rid of that the concentration of the SO3 so the concentration of the SO3 present is now 1,5 moles per decimeter cubed. Calculate the mass of the O2 initially present, and then they give you the Kc value. This is how we go about this. We're going to need to have a balanced chemical equation, okay? So we know this reaction because it's the reaction with SO2 and O2, and it's going to go to SO3. Now, what I like to do is I go, okay, before I start setting up my table, let's just actually see what I had. And it tells me that we have 4 moles of SO2. Brilliant. We have an unknown mass of oxygen, which is actually what we have to work out. They told me that my volume was 2 decimeters cubed. That's important. And then at equilibrium, let's just put it here because this is just for me, 1,5 moles per decimeters cubed. Okay. And then they gave me the Kc value of 4.5. So, initial conditions given. We're then given conditions that represent equilibrium and the Kc value. We definitely need a table. Now, I have one already drawn. Yay, we like this. And we know this is our Rice table. Okay? Remember, you have your ratio. We're going to have initial. We're going to do it in moles. My equilibrium's in moles. And then right at the bottom, this equilibrium is going to be in moles per decimeter cubed. Okay? So, first step, let's write in everything we know. Okay? Ratio comes from the equation. So, there's SO2. So, it's 2 SO2, 1 O2, 2 SO3. Okay? We're happy with that. Initial moles, when we go back to what I wrote over here, we go, well, we knew we had 4 moles of SO2, but actually I don't know how much O2 I've got. But I can't use X. Okay? We can't use X because X represents the grams. So I'm going to make this a Y. Initially, we always have 0 SO3, 0 product. Okay? We don't know about the change yet. At equilibrium, they said to us we have 1,5 moles per decimeter cubed SO3. So this is 1,5. Now we've got to start working backwards. Remember, the volume, that was interesting. The volume is 2 decimeters cubed. We need to, and I'm going to do it in a different color, we now need to fill in the rest of this table. So let's work with what we've got. First, we need to change the concentration into number of moles, because that my second last line is in number of moles. So remember, concentration is number of moles divided by volume. So we have 1.5 equal to number of moles divided by 2. Okay, so we take 2 over and don't do like I did earlier today, and when 2 times 1.5 is 6. I'm not really sure what I was thinking, but the number of moles is 3. So that changes to 3. Brilliant. Now we are so on track. Now, we started with 0, we ended with 3, so the change was I added 3. Now we look at the mole ratio. This line and the change line must be the same ratio, okay? So the ratio line is 2 to 1 to 2. The change line must be 2 to 1 to 2. My ratio for SO2 to SO3, 2 to 2, so that means it's the same number. I can put a 3 there. 1 to 2 means that the one in the middle must be half the one on the end. So half of 3 is 1.5. Okay? Hopefully I haven't lost you. But what do we need to remember? We make products, so we add the change by the products. We use the reactants. Now what I like to tell my learners to do is actually to draw a second line over there, so we remember which side is the reactants, which side is the products. Sometimes we get confused. Which then means to work out the final equilibrium, we've got to go, okay, well, I started with 4 SO2. I've used 3, which means I'm left with 1. Yeah, now comes the fun part. Oxygen, I started with Y. I didn't know how much I had. I've used 1.5, so I'm going to go Y minus 1.5. I'm afraid we can't get away from the ugly maths. Sorry, guys. Kc expression requires us to use concentration. Concentration means I've got to take number of moles divided by volume, which means for all of these, and I'm just going to write it here, I'm going to have to go number of moles divided by volume. So I'm going to have to go 1 divided by 2. The volume of this is 2. So that gives me a half. Eesh, now it gets horrible, because now we're going to have to go Y minus 1.5 divided by 2. Please don't give up, grade 12s. I know it's not nice. Keep going. You've done the hard work. Let's find out how many moles of oxygen we got. Because once I've got the number of moles of oxygen, I can work out the mass. Okay? So, my Kc expression is products over reactants. So now the SO3, the one we did before the break, had this the other way around. Okay? Now the SO3 goes on top because it's my product. So my expression is going to be SO3 squared, and I'm not going to leave any squareds out this time. I'm going to be careful. SO2 squared O2. Okay? They told you that the Kc value was 4,5. Okay? SO3 is 1.5. And that's all squared. The O2 is 0,5, all squared, and this is Y minus 1.5 over 2. Now I'm going to show you a little bit of a trick. Your maths teachers might kill me, but just bear with me, because of course this isn't a maths exam. Okay, so stick with me. I want to get rid of the fraction, which means I'm going to multiply I'm going to take whatever's at the bottom of the fraction and multiply it on both sides. So this is what happens to the equation. So we end up with 4.5 times 0,5 squared times Y minus 1.5 over 2. And that's going to be equal to 1.5 squared. Okay? Are you all following me? I hope. I'm just going to double check my numbers because I've had a bit of a bad number day. Okay, yes, no, we're doing fine still. Okay. How you end up getting to your final answer really doesn't matter, okay? Now, what I'm going to do, I'm going to show you again. I don't want to do any multiplication. Don't want to take my calculator out just yet. I'm going to leave the y minus 1.5 over 2 over here. I'm going to divide both sides by the 4.5 times 0.5. And of course, grade 12s, if your maths is really strong, and I really hope it is, you can leave out all the math steps. If you can get to the final answer without doing all of this, please do. But I would rather you be on the safe side, okay? Because we don't want to make silly mistakes. That means I now have to multiply both sides by 1.5, by 2, sorry. And this gives me 0.5 all squared. And you know what? That gives me 4. I promise it does. You can go work it out, which means when I take that 1.5 over, I get 5.5 moles. So what we have just worked out is the initial number of moles of the oxygen, but that wasn't the question. The question was, what is the mass of the oxygen? So, remember, molar mass of oxygen, O2, is 2 times 16, so it's 32 grams per mole. From grade 9, I wish. From grade 11, you learned that number of moles equals M divided by big M. Okay, so we have 5.5, which is then my mass, divided by 32. We times by 32 on both sides, and we get 176 grams. Okay, it's a big, big value. Grade 12s, what do I need you to get from this? I know I've done lots, and you can see lots and lots and lots of writing. Please don't get freaked out by that. Okay, I know sometimes you get into your exam and you're looking and all of a sudden you've got lots of calculations everywhere. It doesn't matter. Some of these are long, but this is what I needed you to get. You're going to set up what's known as a rice table. Some of you might have learned it as an ice table because you leave your ratios inside your equation. That's fine. It doesn't matter. You've got to set up your equation, write in what you know initially. The big trick here is that 95% of the time, your initial value of any of your products is 0. You will make the products. Remember, we're looking at what happens when it reaches equilibrium. So we put in the reactants, and we wait for something to happen. And then we see what we get at the end. Okay? That means, and then, okay, be careful here, they have to give you something about the equilibrium conditions at the end. Just one of them. They don't have to give you 2, they don't have to give you 3, they don't have to give you 5. Just one. Because working backwards and remembering that either you minus by your reactants and add by your products, you then have to get your change row, this one, to be equal to your ratio row in the way it looks. That's the big one. What a lot of you try and do is you try and get the equilibrium row to be the same ratio as your ratio row, and that's not going to work. At equilibrium, now in the last segment, Phil touched on the whole thing of excess and what gets used up and stuff. Here, I didn't start with the SO2 and O2 in the correct ratio. So one of them would have been in excess, or one of them would have been the limiting reactant, so be careful. You then minus or plus, and then you just go from there. But remember, Kc has to be worked out in moles per decimeter cubed, and they have to see your use of the C equals N over V equation. Okay, you need to show it somewhere, make sure you've got the units, and then just take the maths one step at a time.
Tracy,
Okay?
talking about taking things one
Yes.
step at a time.
Have
we
I lost someone?
No worries. We have a
Okay.
question.
Yes.
I know that you've gone through it, but just for clarification, because it's come up quite often.
Yeah.
When do we know whether to add or subtract our change in mole? And this is by Sergio.
Okay, Sergio, you minus from the reactants because you're using them up, and you add to the products because you're making them.
There you
Okay,
go.
so you minus on the left, add on the right. I think that helps.
That does help.
Cool. Okay, and actually I'm done. So
Okay,
we
so
can
let's
take a break.
then.
Yep.
Okay, guys, so let's take a break. During the break, you can ask questions to clarify. Make sure that you also jump onto Curio. Don't forget how awesome that is, and we'll see you right after the break. Welcome back, Mindsetters. Physical science is what we are doing today. I hope it has been an awesome show for you guys. There is still tons more to go. So keep your focus, guys. Start asking questions, start answering questions. I can see many of you are answering under the posts that are posted on the page, which is absolutely awesome. It shows your utter understanding, which is super great. Some stuff that you can do over the weekend, you can go over these exact questions as well as the ones that your teachers have given you, your textbooks, the past papers. Just make sure that you have covered all bases, so when you walk into that exam, you know exactly what you're doing. Do you know when the exam is, Phil?
It's coming up next week.
Next week? That's awesome.
So it's soon, and we've got some exam revision happening on Sunday, don't we?
Yes, we do indeed.
So, guys, please, get your exam revision going. Okay, guys, please. I see a lot of people saying, okay, I'm going to watch some chemistry. Okay, guys, this is not about watching us. This is about interacting with us, getting on Facebook, talking to Kat, talking to myself. And it's all about actually making your own notes and practicing, guys. Get into those past papers. I can tell you now, don't waste your time making a million summaries. That's not going to get you the marks. What is going to get you the marks? Make a few summaries, read through your notes, put those notes to the side, and start getting into those past papers. Guys, they're all over the web. We've posted them on our website before, and they're available on the Department of Education and on Tutong. They're everywhere, guys. There's no excuse. Practicing past papers is going to make you a better learner in that exam. Okay, so guys, let's get into some of those questions that you guys have been sending in to us. And this was a question from our help desk. And now this was a very, very good question, because now this is getting into this tough stuff about organic chemistry. Okay, so it says, is it right if I assume that when a reaction is in the presence of a concentrated base? Now you think, okay, well, I'm sure that Phil said organic chemistry, and it's talking about bases. What do I mean about bases? Okay, I'm going to start talking about bases and how they fit into organic chemistry. So let's just highlight the important pieces. There we go. So a concentrated base is what we're dealing with. Okay, then it is an elimination reaction. Okay, there we go. There's some organic chemistry. So elimination reaction. Okay. And when it is in the presence of a dilute base, then it is a substitution reaction. Okay? So basically what they're saying is strong base, elimination. Weak base, or at least dilute base, then it's going to be a substitution reaction. Well, let's see if that's actually true. What I'm going to be doing is I'm going to be doing two different examples of the same base with the same chemical, and we're going to get two different products. Okay, so I'm going to keep it nice and simple. Okay, the guys that are studying elimination and substitution and all of this stuff, I want to make sure that you can understand very carefully what I'm doing. Okay, now in this reaction, it's starting off exactly the same way. So what I'm going to do is I'm going to start off with a nice organic chemical, and then we're going to name the thing. We're going to treat it with some strong base, or at least concentrated base, and then some dilute base. Okay, so here's my chemical. I'm going to be drawing a structure. I want to make sure that you guys can name this thing. So I've got 2 carbons in there. I've got a whole bunch of hydrogens. There's one hydrogen. There is another hydrogen. Another one. And here comes the curveball, guys. On this last carbon, I've got hydrogen, but there it is. What I'm going to be doing is in slightly different color, is I'm going to say that there is a Br. So a bromine atom. Okay. Question is, what is a bromine atom doing on here? Well, that is a halide or a haloalkane. So I've taken an alkane and I've put a halogen on it. Okay. Now, we can do some pretty cool stuff with this. Now, anytime you've taken an alkane and you put something different on it, that is called a functional group. The bromo functional group is really, really cool, because what it allows me to do is it allows me to change this molecule. As soon as I put bromine on there, I can do cool stuff with my molecule. Now let's figure out what we can do with it in terms of a base. So there's 2 particular instances that I want to tackle today, and here they are. Okay, so heading off to the left and heading off to the right. Let's start out with a strong, or at least a very, very concentrated solution of sodium hydroxide. So what we're going to do is we're going to say concentrated sodium hydroxide, so concentrated NaOH. Now, that's going to do something slightly different to when we take dilute. Now, dilute NaOH is going to do something very different. So dilute NaOH. Okay. Now, we're going to assume that the NaOH is dissolved in some water, and we're going to see what goes on here. Okay. So concentrated sodium hydroxide. Now, concentrated sodium hydroxide does something very, very strange. What it's actually going to do is, because it's a very, very, very strong base, what it's going to do is it's going to look for an acid. Now, it may not seem like this, but there is actually an acid linked up to this molecule. So what I'm actually going to do is, this is going to be a temporary thing, but just follow through with me. H with Br actually makes hydrobromic acid. Now, you didn't need to know that, and it's not really that important, but I know that concentrated, and this is the way that I remember it, if it's concentrated, sodium hydroxide is very, very greedy. It's going to take everything with it. So what it's going to do is it's going to take the H and it's going to take the Br. So let's figure out what happens when I remove an H and a Br from this molecule. So let's draw it out. I've got carbon, carbon. I've still got my hydrogens down at the bottom. Now, there's a slight difference. I'm drawing them in a slightly different way. Because what happened was, now these two carbons only have 3 bonds. Now, that's not allowed. You can't have 3 bonds on carbon. Now, that is not possible to have neutral carbon with 3 bonds. What that does is it allows me an extra space to make into a double bond. So concentrated sodium hydroxide does remove the H and the Br, and it leaves behind an unsaturated compound. So this is ethene. So I went from bromoethane to ethene. Okay, well, I've gone from being saturated to being unsaturated. And that, to me, is a sign that we've undergone elimination. So whoever asked this question or proposed this is absolutely correct. If I use concentrated base, I'm going to have an elimination reaction. Now, don't forget, guys, there's something which came off here, H and Br. Now, that H and Br actually reacted with my sodium hydroxide. So there's a couple of other products to this one. So what I've got to do is I've got to make sure that an acid and a base in water will make H2O. Now, there's a third product. This is kind of weird. You've never seen this before. So I've got H2O from the reaction between my concentrated base and the HBr. What's left over is also a salt. So what you're going to find is that the halogen will find the sodium very attractive, and they will stick together. Okay. Now, let's just divide this off. So a concentrated base, yes, absolutely makes an unsaturated alkene, so does elimination. Let's see what happens with dilute sodium hydroxide. I'm pretty sure most of you have guessed that this is where substitution takes place, replacement. So I'm actually going to take away this little box, and that no longer is important because we've done it. Now what I'm going to do is I'm going to do something different to the bromine. Now, because there's dilute sodium hydroxide, it acts in a very different way. Because it's dilute, it's not as strong, or not as strong in terms of alkalinity. It's not as basic. Now, because it's less basic, what it's going to do is the OH is just simply going to slip in there and replace the bromine. Dilute means that there's less, and it's less greedy, and it's not actually going to perform elimination. So what you're going to find is that I've got my 2 carbons over there, and the bromine is now going to be kicked out and replaced by the hydroxide. So that was a replacement, and a better name for a replacement in organic chemistry is substitution. Just like soccer rugby players, substitutions are replacements for the originals. So what happened? I've replaced the bromine with a hydroxyl or a hydroxyl ion. Okay? Now the hydroxyl ion or hydroxide ion became a hydroxyl group. You don't need to know those names too carefully, but what I am telling you is that the OH from the sodium hydroxide goes in and replaces the bromo group. What's left over is still sodium and the bromine inside there. Okay, so a lot of organic chemistry in one question, but a really, really difficult and much more sort of higher level thinking question in organic chemistry. Whoever posted that through, well done. You're doing the right types of questions to really sort of stretch you up into those 90%. Okay, now we've got a couple of other questions coming through here. Okay, now it says, which homologous series has a carbonyl? Okay, now a carbonyl group. Okay, and what is the effect of the carbonyl group on physical properties? Okay, now we've got to be quite careful about what a carbonyl group actually is. A carbonyl group is obviously something to do with carbon, but carbon linked up with what? Now, anytime you see the following, a carbon with a double bonded oxygen, that is called a carbonyl group. Now, there's many other things which can be linked off to the side, but a carbonyl group is anything where I've got C double bonded to an O. Okay, so let's answer the first part of the question very, very quickly. So, which homologous series has carbonyl groups? Well, there's actually more than one. In fact, in your chemistry syllabus, there's at least 4 that I can think of just off the top of my head. So let's actually list them, let's draw them out, and let's identify them. It's a great way to revise homologous series. So what we're going to do is we're going to discuss when I've got a carbonyl in the middle of a chain, when I've got a carbonyl at the end of a chain. What happens when I've got a carbonyl linked up with other types of functional groups? What about with an OH? And a carbonyl, once again, linked up with an oxygen. Now, these are all very, very different from each other. So the first one, where it's in the middle of the chain, in other words, it's in the chain, this links up very strongly with the German word for a chain, and that is a ketone. A ketone tells me that the carbonyl is sitting right in the middle of the chain. It's got a carbon and it's got a carbon. It's got 2 friends on either side. So a carbonyl in the middle of a chain identifies this homologous series as a ketone. So that is a ketone. That is the one functional group, and it makes that one into a ketone. Now, what happens when I shift that carbonyl group right to the end of a chain? So what happens if that chain ends off in an H next to the carbonyl? That means that I've got a carbonyl cousin of ketones. Instead of being in the chain, it's at the end. This is an aldehyde. Okay, so very nice. If I can see that the carbonyl is at the end of the chain, that is an aldehyde. Okay, now what I've done is I've actually drawn 2 slightly different carbonyl cousins. Now these ones sometimes are not only called carbonyl, but carboxyl. Now, a carboxyl group is when I combine a carbonyl with an extra oxygen. So this is both a carbonyl, because of the C double bond O, and a carboxyl. So a carboxyl is something which belongs to these 2. So the first one here is a carboxylic acid, because it's got a carboxyl on it. So carboxylic acid. So carboxylic acid is one of those 2. And then the very next one has also got a carboxyl. Now this carboxyl group, but because there's no H on the end, is an ester. And if I remember, I was looking up and down on the Facebook page, and you guys were asking so nicely about the difference between a carboxylic acid and an ester, and here it is. An ester links up with another chain and has no hydrogen on the end, whereas a carboxylic acid has got that OH right at the end there. So I hope that you can see the difference between these functional groups. Okay, now let's answer the second part of this question. So let's just make a little bit of space on here, and let's actually answer that a little bit further down. Okay, so now let's try and compare 2 compounds and figure out how it affects the physical properties. So physical properties are boiling point, the melting point, the vapor pressure, the viscosity, all of these things. How does having a double bonded oxygen on something change its boiling point? Okay, now to give you some sort of idea what I'm going to be talking about is, let's compare one with a carbonyl and one without a carbonyl. So for instance, I'm going to take something like propane. Propane has got no carbonyl. It's just got carbons and hydrogens. Now I'm going to compare it with another molecule. Now, to compare it fairly with another molecule, what we're going to do is we're going to have the same number of carbons, so it's the same chain length. But what I'm going to do is I'm going to put an oxygen in the middle. Now, this doesn't add very much weight or molecular mass to this molecule, but what it does do is it changes the polarity of the molecule. So what I'll actually find is that propane is nonpolar. Now, because it's completely symmetrical, it's completely balanced, it's the same every way that I look at it. So this is completely nonpolar. It's almost as nonpolar as you can get. This next one is not as nonpolar. What I'm actually going to find is that this molecule, because of that oxygen, has got a very strong negative by the oxygen. That means that I've got a plus and a minus side. So I've got a plus by the carbon and negative by the oxygen. This means that this molecule is a polar molecule. Now, if you remember your grade 10 and 11 chemistry about intermolecular forces, and I hope you guys do, I will remember that nonpolar compounds have much weaker intermolecular forces. That would be London forces. Whereas polar can make dipole-dipole interactions. So what you'll find is that something like this, and we've actually got a name for this. This particular molecule is called propan-2-one. Its other name is acetone. And any of the girls out there that have taken some nail varnish remover, acetone is actually a liquid. So let's spell liquid correctly, first of all. Okay, so it is a liquid. That means that the intermolecular forces are actually very strong. Now, propane is a gas. I know this because this is actually a very large part of the gas which I get in cylinders. So this is a gas, and that should actually tell you that the intermolecular forces between propane are much, much weaker than they are between molecules of propan-2-one. Sure, the lesson's flying by, isn't it, Kat?
I know, it really is. It always does when you're having fun.
Absolutely.
So let's take a break. Are you ready, Phil?
Absolutely.
I know that you guys are ready for a break. During this break, rejuvenate, get something to drink, maybe a cup of tea, maybe some water, and we'll see you right after the break. Hello, Mindsetters. Welcome back from that really quick break. We really want to cover everything that you guys need to know. Although we have other days, I know we still have Sunday, so we might not get through everything today, but don't worry. Sunday, there is another show. For those of you who are like, oh my goodness, you guys are only doing chemistry and physics and only science things, don't worry, guys. Next week is a brand new week, and every week we're doing something different. So check out the schedules on the page and go through them, see where you want to get things done and where you don't want to get things done, like physics perhaps. If you're done, what are we doing now? Chemistry. If you're done with chemistry, for instance, you move on to maths, and we have more maths shows next week. So make sure that you cover all the bases, guys, because we're here for you through everything that you need to do. Now, Tracy's laughing at me because I said that we're doing chemistry instead of physics. I mean, really.
Well, you thought we were doing physics, but it's okay.
It's okay.
It's okay.
Science is science.
It's science is science. Guys, we know that you are studying other things. You know, we've had lots of things, and not all of you do science, but the exam school is geared towards the final exam timetable of the government exams. Okay, so you need to bear with us. This is going to be a full chemistry weekend on the channel, simply because you're writing chemistry on Monday morning. Okay, now, like Kakalero said, we can't cover everything, so we're going to cover a couple more questions and then watch the channel, okay? The schedule's up somewhere, I think it's on the page, and it's going to be I'm sure it's on the website, but just so that you can get through, and schedule watching the things you need, because we can't do everything live either, okay? But we do have a very nice question. It's actually a nice one to actually go through just quickly, from Felokazi. I hope I said that right, Sweet Pea. So it says,
Pelo, Gazi.
It's a pelo.
Yes.
It's not an F.
No, it's
okay,
not
it's
an
P. I apparently can't speak any language. Okay, how can I identify which element is going to be at the anode or cathode using standard reduction potentials? This is a great, great question, because it also means we need to know certain things that happen within our electrochemical cells. So before we even get to the standard electropotential, let's first identify for ourselves what happens at the anode. At the anode, we have oxidation take place. So I like to call it an anox. Okay, oxidation takes place. Okay, oxidation. At the cathode, which we'll call we have reduction. Okay? So we have an ox and a red cat because we have oxidation and reduction, which means we need to be able to identify, when it comes to the oxidation, what is the reducing agent. Okay? Because when something is oxidized, so when something gets oxidized, it is actually the reducing agent. Now, I just learned such a cool thing now. I'm very excited. Okay, and we've got to say thank you to John for this. It's the first time I've ever seen this. It's very cool. Oxidation means that we have something that gives away its electrons, okay? Now, way back when I was younger, okay, when something was cool, we called it rad, okay? It was rad. Do you remember that word?
I remember it.
Cool, don't feel so old. Okay, so if it was fun or sick or cool, it was rad. Okay, now I look really stupid. Moving on.
That's okay.
No, it's not. Moving on. It's okay, my kids are going, no, that's what it looks like in class. It's fun. Okay, rad means reduce. So it's reducing agent. Reducing agent donates. So your reducing agent is your rad agent. Okay, he's the nice one. It's like a James Bond undercover agent who's the good guy. Okay, because he donates, he gives, he's brilliant. Okay, then oxidation. If something is reduced, it means that it is the oxidizing agent. Okay, and now we remember that reduction means that it's going to lose an electron. So you know what? It's actually been a bit of a stupid person. Well, it's been a bit silly, and we can't really call it an oak, like in Afrikaans, but we can call it an oat. Okay? Now it's an oat because we now have our oxidizing, so that's the O, oxidizing agent takes. So he's the bad agent. Okay, he takes things, not good. Okay, so your oxidizing agent is when reduction happens. The reducing agent is when oxidation happens. Now, how does this help us understand electro potential table? Because right now you go and trace this, so hasn't helped us. Watch. I'm going to find my redox table. Now, on the redox table, this value, these voltages, tell me how good or how bad it is at reducing or gaining electrons, okay? So now, remember, reduction or the reducing agent is the agent that is oxidized, it gives away, okay, which means it gives its negatives. So the more negative it is, the better reducing agent it becomes. Okay, and if it's a good reducing agent, then it's going to be oxidized, and if it is oxidized, then it is the anode. Okay, so we look at the negative. If we look further down and we start looking at the ones that are positive, okay, if I don't lose my pen, here we go. Okay, now we start getting positive values. The more positive it is, the better it is at being an oxidizing agent. Okay, and if it's a good oxidizing agent, then it is going to be reduced, so it makes it the cathode. Okay, so what does that mean if we go back over here, which is, nope, that was full. So in other words, your oat, which is your oxidizing agent, so it's where reduction takes place. So your oat, now I'm moving things that I don't mean to. No, go back. The board is fighting with me again. Just so you know. I think it's very rude. Anyway.
Actually, it's a good person.
What?
The board.
Anyway, so Otis reduction, which means the oat is the cathode. And cats don't eat oats, but let's pretend. Okay? So you got a red cat which eats oats, and your oxidizing agent becomes the anode, so it's an ANRAD. So it's a red cat that's rad. No, it's an ox that's rad. Never mind. You get the point. Okay, now Kathleen really is actually giggling at me because I'm being a bit silly right now. But the point is, you know which oxidizing agent is going to be by looking at the the voltage. Okay, very negative means that it's going to be oxidized, so it's going to be the anode. Okay, anode is where oxidation takes place, so anode is your negative, or the least. It's got the smallest value of the voltage. Okay, and this is for spontaneous reactions. Your cathode becomes the bigger of the voltages. Okay, now we need to quickly tackle one more question. I'm going to do this in like 2 seconds flat. The thing you all hate, the Maxwell-Boltzmann curve. Okay, so you get, and this is a temperature curve, remember this comes up in rates. On this axis, most of you are okay with the fact that this is going to be kinetic energy in kilojoules. This axis is either going to be labeled percentage of molecules or fractions. Okay, fraction of molecules. Now this is what, and I've got like 2 minutes. Be very careful, and then you've often got a line here which represents the activation energy. This curve, if I take the area under that curve, that gives me the total number of particles in the system. Okay? If I wanted to say, now look at this, this is the highest percentage, and it's got a certain value, but this percentage may only be 50. Can't be 100, it's got to be less than 100, okay? But that might only be 50. Now what that means is, say we only had 100 particles, this tells me that only 50 of those particles have this kinetic energy, okay? Maybe down here, this is only 10. So this tells me that 10 particles here have that kinetic energy, and then I have 10 particles over there, and all what's underneath this area, that total number of particles in that area, which have energy greater than the activation energy. Because I look at the area under the graph. Don't look at the value, okay? The area under the graph. If I change the temperature of the system and I make it hotter, okay? Remember, temperature is the average kinetic energy. This is what happens. It becomes flatter, but shifts over, okay? The area under this graph is the same as the area under the white graph, okay? So you've really got to look carefully at that, and I'm afraid I've run out of time. Darn. Remember, if we need to, we can cover it again on Sunday at the next live show. Just send the question in again. Okay.
You don't have a sentence to finish?
No, I'm done.
Okay.
Sorry.
Cool. Okay. So guys, Tracy's done, but she will be back on Sunday. You will, hey Tracy?
I'll be here.
Exactly. So you can hold her on this question or hold on another question. Send through your questions, guys. There's the help desk at Learn Extra where you can send through everything that you need to send through so that they can go through on Sunday. Good luck for your exams, guys. I know that this weekend is a study hard weekend for you science folks, and I wish you all the best. Remember that you can still ask questions, as I've just said, so keep doing that, guys. Learn more and learn extra. Bye, guys.